Hi, good morning, students. So, with the last class, we finished our electrostatics, complete electrostatics topic. So, I think it took nearly 39 or 40 classes. So, now we are starting this current electricity, and so which is an easy topic, and some similar calculations will be there, which we discussed in heat transfer. So, not all, some calculations, like there we discussed some thermal resistance calculations and the series and parallel combination of the rods, and here also such a similar concepts will be there, not all, what I am saying, right? And so now here, so let us see about this current electricity. So in this current electricity, we discussed previously like about the static, and now we are going to discuss about the electric current. So now when we are taking this a conducting material, suppose if I consider an iron rod I am taking here, and so now we know there is no any external connections for that iron rod, just if we are taking an iron rod. So can you say is the electrons present in that iron rod remains at rest? Free electrons, we are talking about the free electrons only. As we know, it is a good conductor, that means it is a metal, it consists of very large number of free electrons, right? Now is those free electrons are at rest, they remains at rest? So that definitely you can say that they are not at rest, right? Because even at the room temperature they possess some thermal energy because of this temperature, and so because of that thermal energy they are randomly traveling throughout that material. When the electrons are traveling, then why there is no current flowing through that conducting rod here? So now I am concluding the electrons are not at rest at the room temperature. If the rod is at the room temperature, for example, when the electrons are not at rest, again my question is, now why there is no current flowing through the conductor? Because those electrons will move randomly through these materials, like our in gas kinetic theory of the gases we discussed there, molecules of the gases will move randomly throughout those materials, right? Throughout this container, and while moving they make the collisions with the neighboring molecules, and they make the collisions with the walls of the container also, right? And so here also the electrons, the free electrons will move randomly throughout those throughout the material, or throughout the volume of the material, and while traveling they make the collisions with the lattice ions, or they may collide with the neighboring lattice ions or atoms, and so then such a collisions will take place, and so they deviate their path there. And so now here on an average, that means what I am saying is here the electrons will travel randomly throughout these materials here, they follow some zigzag path here, and so that if here if I am taking a cross section here, if I am taking a cross section at any instant of time, the number of electrons traveling from left to right are exactly equal to the number of electrons traveling from right to left, and so that there is no any net charge crossing this cross section. Got it? In conductors means, you know, only electrons can move, only charge carriers are only electrons, right? And so now at any now what we are discussing is those electrons will be moving randomly throughout this material, volume of the material. So at any instant of time, the number of electrons crossing from left to right are exactly equal to the number of electrons traveling from right to left, and so that there is no net charge flowing through this cross section, right? When there is no net charge flowing through the cross section, we say that no current is flowing through the material. So that is the reason why there is no current flowing through the materials, even the electrons present in the material are not at rest. So if you are taking just an iron rod, then inside that iron rod the electrons will be randomly moving, no doubt in that. But the current is not there in that iron rod when no external connections are there, in the sense the net charge flowing through any cross section will be zero. If suppose say 100 electrons are traveling from left to right, then at the same time 100 electrons will travel from right to left, and so that the net current will cancel. That means net charge flowing to any cross section will be zero, and so net current is also zero, right? And so now basically this current is nothing but it is The current we can use in many senses. Just if you are taking it as a current means fluid current or wind currents, we can use like that. That means anything flowing, current in the sense. Now if electrons are flowing, then the rate of flow of electrons is nothing but generally we define the current. So like suppose here if you are doing some external connections, if you are applying some any external field here, if suppose some external field is applied to this conductor like this, now all the electrons present in the material will experience a force, right? And so they will experience a force opposite to the direction of this electric field. And so all the electrons will start accelerating along this direction, right? And so when all the electrons are accelerating in that direction, even that means whatever the cross section you are taking, in that across the cross section there is some net amount of charges flowing when you are applying electric field. Before applying electric field, no doubt net charge crossing this cross section will be 0. Next what we are taking is, suppose we are applying some external electric field to such a conducting material. When you are applying such an external electric field, the electrons present in that material, all the electrons present in the material will experience a force opposite to the direction of this electric field. So all the electrons are accelerating along this direction. So all the electrons have an acceleration along this direction in the sense, definitely there is certain amount of charge crossing this cross section in the given time interval. And so now therefore this current can be defined as, so first I am defining this average current here. So average current can be defined as this I average is equal to the total amount of charge flowing per total given time interval. Suppose in the 5 seconds of time interval I am checking how much charge is crossing the given cross section. Then suppose if 10 coulombs of charge is flowing through this given cross section in 5 seconds. So 10 by 2, the given time interval, in the 5 seconds interval we are calculating here. So that we define as average current, right? Or simply we write that as Q by T also, where Q is the current flowing through that, charge flowing through that, and T is the time interval there. And so that means that is our average current there, charge flowing through the given cross section per total time interval. And so then from this you can say that the unit of this average current is nothing but, from this definition you can write this as coulomb per second. And so that coulomb per second only we call this as ampere, so which is represented with this A. So that means ampere is a SI unit of this current. And now this ampere, you know, ampere is one of the fundamental quantities in SI. In system of international, there are certain fundamental quantities, you know. So in that, this current is also the one of the fundamental quantity there. And so its SI unit is A, and which is nothing but this ampere per second. And so I can write this 1 ampere per second, 1 coulomb per second is equal to 1 ampere. Those are equal. That is the meaning there. And so now that is the average current. Now suppose if you want to define the instantaneous current. So the instantaneous current we can define as, so instantaneous current. So instantaneous current in the sense this I is equal to, we write like limit delta t tends to 0, delta q by delta t, right? That means when delta t is tending to 0, when time interval is very small, then almost you can consider it as a point of time. So right at the instantaneous current is nothing but current flowing at any particular point of time or instant of the time. And so this can be expressed as, we write this equation as dq by dt, right? That we know already. When delta t value tends to 0, then this delta q by delta t can be replaced with dq by dt here. So now this is nothing but our instantaneous current. And from this only we define this current as rate of flow of charges here. So rate of flow of charge is nothing but our current. And so now which is the unit is defined here already, this coulomb per second or ampere, and that ampere is we call it as a SI unit there, which is represented with the A. So now write the definition here for the current. And about this mechanism we will discuss again when you are discussing about this drift velocity. About the drift velocity, how the electrons are drifting, we will discuss there. So now I am not giving any information regarding this. So directly I am defining the current here. So write that the average current flowing through the given cross section, the average current flowing through the given cross section can be defined as total charge, can be defined as the ratio of total charge flowing through the cross section, total charge flowing through the cross section to time interval, ratio of total charge flowing through the cross section to time interval. Therefore, write this: average current I average is equal to delta Q by delta T, and the unit is coulomb per second, or which is ampere. Now the instantaneous current. So just first write this expression: I is equal to delta limit delta T tends to 0 by 0 dq by delta Q by delta T, that is equal to I is equal to dq by dt. So after this write the definition. Therefore, instantaneous current or current can be defined as a rate of flow of charge. Can be defined as the rate of flow of the charge. Right? So that is expression there. That means we write this as dq by dt simply. And now let us see some information of some important points regarding this current here. So write them point wise after this. So the first point what we can discuss is about the whether the current is a scalar or vector. About the unit we discussed already or mentioned that ampere is a unit of the current. I'll write it that as a first point. Ampere is a unit of the current, and a current is one of the fundamental quantity in SI. Current is one of the fundamental quantity in SI. Right? Next point. So can you say whether the current is vector or scalar? I think you have an idea about the current already. Suppose if a simple circuit, if I connect like this, and in vectors itself I explain in detail about this. Suppose now I am taking this AB conductor. Now a battery is connected like this. Then we know current flows from positive terminal to negative terminal here, that we define the direction of the current. And so now here we are taking this, suppose I am taking this as some 2 amperes current is flowing here, for example, right? And so now 2 amperes is the magnitude of the current, and we are defining this as current is flowing, it is having magnitude as well as direction. So now can we define that as a vector? So absolutely no. The reason we discussed already. That means we can say that it does not follow the vector laws of addition, or we can say that the direction given to this current is not the original direction. This is the conventional direction of the current there. So basically we can say that it does not follow the vector laws of addition. Vector laws of addition, simply I can explain like, if suppose 2 conductors are joining like this. This is say carrying 2 amperes current, and this is 3 amperes current, right? And so the net current we can say it as, in general also we can say, and later we define that as a Kirchhoff law. And so in general we can say that as the net current will be 5 amperes we can say, right? Now here whatever may be the angle between these 2 conductors, those 2 wires, you will get this net current as 5 only. So if it is a vector, it should not be like that. The resultant should depend on the angle between these 2 vectors. We know the force. If the force is acting like this, one force is acting like this, the other force is acting like this. Now the resultant force, this is F1, let us cancel. Now the resultant force will depend on the angle between those 2 forces here, both magnitude as well as the direction of that resultant force will depend on that angle between those two conductors there. But it is not the case in case of current here. It does not, the resultant current does not depend on the angle between those two wires, right? And so that means it doesn't follow the vector laws of additions and vector laws, and so we consider this as a scalar. So mention that as a second point there. Current is scalar. Because it does not follow the vector laws of addition. That is the reason why, even though it is having this direction means. And the next one what I can write is direction, about the direction of the conventional current. So that means I am saying about the direction of the current. Direction of conventional current. So in that mention that the direction of flow of positive charges, the direction of flow of positive charges is taken as the direction of the current, or opposite to the direction of the negative charges. That means current direction of the conventional current is nothing but in the direction of positive charges, in the direction of flow of positive charges, or opposite to the direction of negative charges. So first mention that, I will explain that direction. The direction of conventional current is, the direction of conventional current is in the direction of flow of positive charges, in the direction of flow of positive charges, or opposite to the direction of flow of negative charges, opposite to the direction of flow of negative charges. That means now if current in a conductor is represented like this, if current is represented like this, then what actually meaning is the positive charges in this conductor should move either in this direction, or the negative charges in this conductor should move along this direction here. So that means, or both may be present depending on the medium, depending on the material which we are taking here. If it is a conductor, for example, if it is a metal wire is connected across this battery like this. In the previous example, if a metal like a metal wire is connected, the conducting wire is connected across this battery like this with some resistance R, and about that resistance we will discuss later. And so now this connection, suppose simple connection if I am taking like this. Now here we represented the current direction like this from A to B. So but what actually the flow is taking place here is electron flow will take place, and the electron flow will take place from this negative charge to positive charge here. And so these electrons are flowing like this here. Large number of electrons will be there, and those electrons are flowing from this positive, negative to positive terminal, which is opposite to the direction of the current flow here. So that is the current direction of the current means we should remember that point. Positive charges, if the positive charges are flowing in that material, then they will move in the direction of the current, and that means that the direction is taken as the current direction, or opposite the direction of the flow of the electrons or the negative charged particle. If any other negative ions or negative charged particles are there, so opposite the direction of flow of such a negative charged particles is taken as the current direction there, right? So this is the direction, that is about the direction of the current. And next here about this current we can say type of the charge carriers. And we know basing on this electrical properties we discussed already in the electrostatics topic, like the materials are classified into different types, like we defined already conductors, insulators and semiconductors. And so now here in the different materials, let us say about the what type of charge carriers are present. And in the conductors we mentioned already, in the conductors the charge carriers are only electrons, because it consists of large number of free electrons. In case of insulators, all the electrons will be involved in that bonding, and so that no free electrons are present inside these insulators, and so that the conduction is not possible there. And even if you are applying some high potentials, and if you are rising the temperature of certain materials, and if you are applying some high potentials, then insulator may become a conductor. That is a total different phenomenon, and we discuss in the actually we discuss such a concepts in capacitors, breakdown of the dielectric, breakdown of the insulator, that we called as the breakdown of the insulator. That means every insulating material will act as insulator up to certain potential difference. If you are applying the potential difference beyond that, more than that, then it may become a conductor, because the bonds involved in that material may break down. So when the bonds are breaking down, then automatically the number of charge carriers will be created in that. That means number of charge carriers will be developed in that. And so as the charge carriers are available in that, it may act as in conducting material. So that is a total different phenomenon, and we will discuss later. So that means insulator means, as of now, under normal conditions, insulator means it doesn't consist of the free number of large number of free electrons, and so that it doesn't allow the electric current to pass through them. And next, in case of semiconductors, if you consider, in case of semiconductors, can you say what are the charge carriers? I think all of you have an idea about the semiconductors in your 9th or 10th classes. Like semiconductors means, there we will discuss in detail again. A separate topic is there, as I said previously. And so here simply about the charge carriers we are discussing here. In semiconductor, two types of charge carriers will be there. So one we consider it as a electron, which we know already, negative charged particle, and we consider it as another positive charged particle here. That positive charged particle is nothing but we call it as a hole. The hole is nothing but the deficiency of the electron there. This is an electron, one negative charged particle, and a hole. So due to both the charged particles, so we say holes and electrons, because the charge carriers in semiconductors are holes and electrons in case of semiconductors, right? So charge conduction, that means electric current will flow of the electric current will take place because of these two, holes and electrons. And a hole is nothing but simply the deficiency of the electron. Deficiency of electron means simply we know when you are removing an electron from a neutral atom. Suppose let us take any neutral atom from oxygen, for example, oxygen atom, if you are removing one electron, then it becomes oxygen ion, that means negative ion, right? Because there is deficiency of if you are removing electron, then it becomes a positive ion, right? Because there is a deficiency of electron. So the deficiency of electron will give some result some positive charge there. And so this hole is also considered with the deficiency of this electron there, and so it is assumed to be carrying some positive charge. Actually nothing will be present at the hole. So we will discuss about the later. So here just we need to remember it as the charge carriers in semiconductors are both holes and electrons. In conductors, only electrons, right? In insulator, then there are no charge carriers inside these insulators, are negligible. And next some other like gases if you consider. In case of gases, both ions and electrons will be, electrons are the charge carriers there. So that means when ionization takes place under air, that means air if you consider under the normal conditions, then it behaves like a insulator only. Otherwise, these electrical cables, what we are saying in our roadside, they can't be in air, because if air is a conducting medium, we will definitely get the shock from those wires. So we are not getting the shock in the sense we can clearly say that air medium is a non-conducting medium under normal conditions. As I said, if you are applying high potential difference, then it becomes a conducting. As I said, the breakdown will take place, which is an example for that is a thunderbolt. So when the thunderbolt is appearing, this air will become a conducting medium, right? And so that means if you are applying such a large potential, an insulator may break down, and so it becomes a conductor. And so in case of gases, as I said, in case of gases, such a charge conduction may take place because of these ions and electrons, right? Because when ionization is when ionization is taking place, electrons will come out of these atoms, so that these electrons and positive ions will be there. So due to that, that conduction will take place in gases. And next, in case of electrolytes, if we consider, we know the electrolysis process. So in case of electrolyte, the charge conduction, that means electric current will flow because of both positive and negative charges. So those are the types of charge carriers here. Next, mention about these charge carriers. The charge carriers in conductors are only electrons. The charge carriers in conductors are only electrons. Next, the charge carriers in semiconductors are both electrons and holes. Both electrons and holes. In brackets, write hole means deficiency of electron. Deficiency of electron considered as positive charge. Right? Come on, next. The charge carriers in gases are electrons and ions. Electrons and ions. Next, the charge carriers in liquids are, that means we can say electrolytes. The charge carriers in liquids are both positive and negative ions. Both positive and negative ions. So those are the types of charge carriers there, right? And next here, when they actually, in case of current, we can define like this. If suppose Q is the charge flowing through this in a time of t. So let us write this as a next point. If suppose here I am saying n number of electrons are crossing that given cross section in the time interval t, then current flowing through that we can write it as n into E by t, right? And so this n by t, suppose I am taking this as number of electrons crossing per unit time, and you can simply write this current as Ne. So right, so where n is, where small n is equal to capital N by t, is number of electrons flowing per second, flowing through the given cross section per second, right? So now write that as the next point in that. If n number of electrons are flowing per second through the given cross section, then current flowing through the cross section is given by, so just write this expression, I is equal to Q by T. That Q we are writing as Ne, which we know already in electrostatics. And so now this N by T we are taking as small n, number of electrons flowing per second. And you know the E value. So 1.6 into 10 power minus 19 coulombs. And it's a magnitude of the charge here. And now here, and from this we can calculate how large that 1 ampere. So 1 ampere means, let us say, how many number of should cross the unit, that means should cross the given cross section in the unit time. So now for 1 ampere current, 1 ampere current, so let us say this, I can write this as I is equal to 1, that is equal to N into 1.6 into 10 power minus 19. Therefore, this N is equal to 1 by 1.6 into 10 power minus 19. So I can write this as, think you will get this expression as 6 point, so this is nothing but I can write this as, you can just simplify this, you can write this expression as like 19 10 power plus 19 by 1.6, or which is nothing but 10 power 20 by 16 you can write, or which I can write this as 100 by 16 into 10 power 18. Now we can simplify this, 4 4s and this is 4 25s. So then 25 by 4 in the sense it is 6.25 we can write into 10 power 18 per second. That means what we can write is this 1 ampere current means to flow this 1 ampere current, the number of electrons crossing the given cross section must be equal to, for 1 ampere current, this is nothing but for 1 ampere current 6.25 into 10 power 18 electrons per second should cross the given cross section. So that means you can observe this how large that 1 ampere means. So 1 ampere current means it's a very large current only. And so that means this number of this 10 power 18 number of electrons are crossing that cross section in 1 second. So that means such a huge number of electrons are flowing or required to produce this 1 ampere current there. So that is the meaning of this 1 ampere. You should remember this number also. And so next year, and we can also write like whenever charge is, that means some current, variable current is given, time dependent currents are given. So we need to calculate the charge flowing through that. So charge flowing through the given cross section we can calculate like this. So that means now next mention that next point. If current flowing through the given cross section is given, if current flowing through the given cross section is given, then we can calculate amount of charge flowing through the given cross section, amount of charge flowing through the given cross section in the given interval of time, as so just write this. We are taking this I is equal to dq by dt, and now this dq is equal to I into dt, and from this we can take this q is equal to integral of I into dt, and whatever the time limits are there, in suppose say 2 to 5 seconds for example, if you want to find, then 2 to 5 we need to take the limits, or from 0 to 10 seconds if you want to find, then you can take 0 to 10. So whatever the limits we need to consider, whatever the required data question is there, we can substitute those limits there according to the given question. So we can calculate the charge like that. And I will give the problems based on all this once after completion of this, some important points related to that. We are going to write some expressions based on this. And next let us see current due to this orbiting electrons. Current due to orbiting electron. Right? Write this as an explained only in that. That means with different important expressions will be there based on this. That means here, for example, if I consider in hydrogen atom, or you may consider in any atom, let us consider here. In hydrogen atom means one electron will be there. So I am taking an example of this hydrogen atom here. So here this positive charge will be there here, and this negative charged electron is revolving around a circular path here in a circular orbit, right? And so now we need to define how much current is there due to this flow of this electron here. So then in that case what we can write is, we define like average current only. Average current means the total charge per total time interval we can write. And so then I can write this as q by t. And so this value I can write this as E by this t. So if you know the frequency, this we can express in different ways here. Or this can be expressed as E into F. So where T is the time period of electron, and we know this F is equal to 1 by T, frequency of the electron, right? And instead of this frequency, if angular frequency is given, if omega is angular frequency, then I can write this as omega is equal to 2 pi by t. Therefore, this current I can be expressed as q by, sorry, E by, we are taking that as E by 2 pi by t. Sorry, t value we need to substitute there. So then t value if I substitute 2 pi by omega we need to substitute here. We are replacing this t value from this expression, right? So the t value from this we can write this as 2 pi by omega. And therefore this I value you can express it as E omega by 2 pi. So depending on that given information we need to write this. And now the same expression you can also write, sometimes they may give this speed of the electron and radius of this orbit. So let us see in terms of the speed of electron and radius of the orbit. If v is speed of electron, v is the speed of electron, and r is radius of orbit, right? Then we can write the time period. The time period of the orbit we can write as, time period of this electron we can write as total distance 2 pi r by speed of this electron we can write. And therefore you can substitute the t value here, then you will get this expression for this current. Therefore this current I can write this as E into V by this 2 pi r. So that means all these are expressions for this current due to this orbiting electron only. Depending on the given information, you need to take this expression, suitable expression. If time period is given directly, you can substitute this value. If frequency is given, you can write directly E into F. And if suppose say angular frequency is given, then E into omega by 2 pi we need to write. If velocity, that means speed of the electron and radius is given, we need to substitute that expressions there. And in many problems, generally they will give this omega expression, so we need to remember this expression now. And in magnetism also, in electromagnetism also, this type of applications will be there. That means we need to calculate the magnetic fields also due to that such a orbiting electrons. So for that you need to calculate the first current. And so then this is a current calculation due to this orbiting electrons, right? Now instead of this electron, now suppose I am taking this as a ring. A non-conducting ring on which some charge q is distributed. I am taking that now like that. So now take this, write it as an X point in that. So here I am taking a charge q is distributed on this ring here. A charge plus q is distributed on this ring of radius say r. Now our question is, if the ring is rotating about its own axis, with angular velocity omega, we need to find the current flowing in that path. So write that information. A charge q is distributed on a non-conducting ring of radius r. So charge q is distributed on a circular ring of radius r, which is rotating about its own axis, with angular velocity omega. Then find current due to this ring. So here again we write this simply, we can directly apply this as q is the charge distributed on that. By for one complete rotation you can consider it as t. The t value I can write this as 2 pi by omega. And so then q omega by 2 pi. You can directly substitute that expression here. So this current, that means current flowing in the path of this ring only. So actually it is a non-conducting ring. Current is here, current is not flowing inside the ring here because of this charge distribution. Here if I consider this small element of the charge dq here. So now the dq is flowing like in this dq is following the circular orbit here, like same as that of our electron, right? And so that now the current due to this means dq by this value we need to write. That means dq by t we need to write. Such a large number of elements are there. If you integrate that dq value, then dq by t is nothing. Integral of dq by t is nothing but you will get q by t. So directly I am writing this expression here. So you need to consider this as a small element, and now that element can be considered as an electron, like similar to the previous concept here. So this element is for traveling along this path here, like an electron is revolving in a circular orbit, right? And so then the current due to that element is nothing but dq by t we need to write. Current due to that small element. Now to find the total current due to the entire ring, just we need to integrate this. Then q by t will get, so directly I am taking that q by 2 here. So we can write like this. So it is the current flowing due to that ring here, and such a non-conducting ring is rotating. Next, simply I will give some problems based on the concepts which we discussed till now. So you can solve those problems easily. So write the first problem. Like I am taking this like a discharge tube here. So in a discharge tube, suppose say some positive charges are traveling in one direction and negative charges are traveling in opposite direction here. Right? Now the current flowing through that we need to consider. So write that problem. In a discharge tube, so write that number like 2 into 10 power 16. In a discharge tube, 2 into 10 power 16, singly ionized positive ions. Singly ionized means only plus E. The charge on this will be plus E. If it is doubly ionized, then plus 2E we need to consider, right? So that I am taking it as singly ionized. So singly ionized positive ions crossing the given cross section per second. From left to right. Next. And same number of electrons are crossing the cross section per second in opposite direction. Then find net current flowing through the discharge tube. So that means the given information is positive charges are flowing like this and negative charges are flowing, and they are same in number. So that means here you should remember our direction of the conventional current here. So the current is nothing but, now the current due to the positive ions will be along this direction, right? Current due to the positive ions, because if the current is in the direction of flow of the positive charges or opposite the direction of the negative charges. So negative charges are flowing like this, and so current due to the negative ions will be in opposite direction. So this is the current due to positive ions and this is the current due to negative ions. Now both are in the same direction. Current due to positive and current due to negative are in the same direction. Therefore, this net current I can write as current due to positive ions plus current due to negative ions here. So current due to positive ions will be equal to, I can write this as Ne plus this is also Ne because both the ends are same here. So then this is 2 into 2 Ne we can consider here. So you can substitute those values here. 2 into 10 power 16 into 1.6 into 10 power minus 19. So I can write this as 6.4, right? So 6.4 into 10 power minus 3 amperes. So the current will be equal to 6.4 milliamperes. So that is the current flowing through this given cross section. Similarly, write the next problem. So that means there you should observe that when the positive and negative ions are given like this, they are traveling in opposite direction. So the current due to both of them we should add here. So you can't answer that net current as 0 because equal and opposite charges are crossing each other. So net current is not 0 because the current due to both the positive and negative ions will be in the same direction. So we should add them. So similarly, write the next problem. The current flowing through the conductor varies with the time as 10 plus 2t. 10 plus 2t amperes. This total value is amperes. Then find charge flowing through the given cross section. Find charge flowing through the given cross section in first 4 seconds. In first 4 seconds. Also find how much constant current should flow. How much constant current should flow through the same cross section such that same amount of charge flows through it in the 4 seconds. Same amount of charge flows through it in the 4 seconds. That means this is a conductor, let us consider here. Here we are taking some cross section. So now in the 4 seconds, how much charge is flowing to this cross section we need to consider here, right? So then I is equal to 10 plus 2t is given, and which we know we can write it as dq by dt. And therefore this dq is equal to 10 plus 2t into dt. And then now simply integration. So now here it is from 0 to 4 and this is from 0 to q. Therefore this q is equal to 10t plus t square. Integration, directly I am writing 10t and t square. 2t is t square by 2, then 2 will be cancelled from 0 to 4. And so therefore it is 40 plus 16. So it is 56 coulombs, right? So 56 coulombs charge is flowing through the given cross section there. Now our next question is, how much constant current should flow through the given cross section to allow the same charge to flow through it? So that means in that case what we can write is, I can write this I is equal to q by t, simply we can write here. So that means now it is a constant current. The amount of charge required is nothing but 56. That is the charge should be flowing through the given cross section in a time interval of like say 16. And so then we can write this as so this charge is nothing but you can this is, so this is the this you will get in amperes because this is directly in coulombs and the time we are substituting in seconds only. If it is so then this is the current flowing through that. That means here the question is, you need to understand it clearly. If constant current is flowing, here the given current is time dependent current here. Time dependent current in the sense, so then when time dependent current is flowing, the charge will be varying at the different instants. the different instance of different time intervals. If first 4 seconds we are getting like this, in the next 4 seconds if you are considering, you will get different amount of charge. But when the constant current, that means here you will get like say 14 amperes. If this 14 amperes current is flowing through this cross section here, in any 4-second interval if you consider, the amount of charge flowing will be same, you will get 56 amperes only will get, right? That means you may consider from 0 to 4 seconds or 4 to 8 seconds or 8 to 12 seconds. Any 4 intervals if you are any 4 seconds if you consider, or 10 to 14 if you consider, the charge flowing through the cross section will be 14. That is the question what they are asking. How much constant current should flow such that the amount of charge flowing through that will be same as that of charge flowing in the first 4 seconds. So that means that is the constant current. 14 amperes will become the constant current there. So like such a simple problems you can solve basing on these concepts now, right? So in the next class I will discuss about the drift velocity and the current density concepts, and after that we can discuss some problems based on them, based on the drift velocity and current density concepts. Thank you.